The purpose of this video is to review electronegativity, bond polarity, dipoles, kind of all those related features. So let's start with a molecule. And let's say we have hydrogen. And we know hydrogen, each hydrogen here would contribute one electron. So we would have two electrons here. And this makes sense, right? We draw out a Lewis dot structure. These two electrons form the bond. So if we start talking about electronegativity and polarity, what we're trying to look at is this bond and how do these different atoms of hydrogen share? What is the level of the sharing of these electrons? So one of the things that we covered in class, we said, okay, if we're looking at any kind of a molecule that's diatomic, so H2, Cl2, O2, it doesn't really matter what the electronegativity is, because we know that since they're both the same and they're sharing the bond, the sharing of these electrons will be the same. So let's prove that. If we look at chlorine, let's look at chlorine. We have chlorine, and we know each chlorine has 7 electrons. So times 2 equals 14 electrons. If we draw a Lewis dot structure, okay, and each one has a stable octet, and we're good to go. Now, if we look at a table that has electronegativity information, chlorine has an electronegativity of 3.0. So if we wanted to look at and determine if is there polarity, is there an uneven pulling of the electrons on this bond, well, we do 3.0 minus 3.0 equals 0, which is what we'd expect. And we would say this is a pure covalent bond. Okay, and there's absolutely no polarity. Right, so it's this equal sharing of the electrons. Now let's look at something slightly different. Let's look at HCl. And in this scenario, we would have 7 electrons from the chlorine. We have 1 electron from the hydrogen. That'll give us 8 electrons. Let's draw a Lewis dot structure here. So this looks good. Chlorine has our stable octet, hydrogen a stable duet. And now we want to look at this bond here. Okay, so if we have a table here, the electronegativity of hydrogen is 2.1, chlorine is 3.0. And what we do in these problems, we just take the largest number and subtract the smaller number from there. It doesn't really matter. It's an absolute value. So we end up with 0.9. So if we have this bond polarity, we've calculated to be 0.9. This is in that range that we called polar covalent. So it's a sharing of these electrons, but it's not equally shared. And as we would expect, and again from our periodic trends of electronegativity, this chlorine is pulling on those electrons much harder than the hydrogen is, and it's not a perfect sharing of those electrons. And remember when we do those electron density clouds, it's kind of something like this. Right? The electrons are more around the chlorine than they are around the hydrogen. Now, some other things we can say about this. We said, okay, there's a polarity here. We can also look at partial positive, partial negative. And we said there's going to be these partial charges, these effective charges here, because those electrons are being pulled more by the chlorine, so it has a negative charge. And usually the atom that can become an anion usually has the negative charge, the partial negative charge. And right, the more electronegative is going to have this partial negative charge. We can also draw a dipole, and we would draw it like this, okay, which represents this negative, partial negative charge on the chlorine, and it's showing that the chlorine is not going to share those electrons perfectly well, and it's going to pull some of the electron density towards itself. The last item related to this is regarding geometry. So here we've been looking at bond polarity. Now what we want to do is try to predict the polarity of molecules. And so this is when we're looking at molecules. And we kind of have some rules. We have to look at symmetry, and we have to look at bond polarity. And when we're looking at these molecules, they'll have more than one bond. So let's do one of my favorites, a classic example, H2O. We must start with a Lewis dot structure. And so we know each hydrogen has 2 electrons. Each oxygen has 6 valence electrons. And we get that from the periodic table. Total of 8 electrons. And if we go to draw this out, recall that we said this is a bent structure. It's a bent structure. And the issue are these unbonded electrons that cause this bent shape. Right, so this is an uneven shape to the molecule. Now we would want to look at bond polarity. So we could predict it, but let's actually also calculate it. Oxygen has an electronegativity of 3.5. Hydrogen has an electronegativity of 2.1. Hydrogen has electronegativity of 2.1. Okay, and so if we subtract these, each bond will have a polarity of 1.4. And we're going to have these dipoles, right? These dipoles are going to be going this way. And then we've got these unbonded electrons. So it's not symmetrical. Bonds are polar. Therefore, it will be a polar molecule. In general, when we have these unbonded electrons, we're going to have polarity issues. Something that comes up in class all the time is, does it matter where these unbonded electrons are? And yes, we are looking at this central atom. So, let's look at another example. Let's say we have something like this. Sure, there's unbonded electrons here, but we don't really care. What we are caring about are these, because this is what affects the shape of the overall molecule. So don't be confused by these unbonded electrons on the outside. Let's look at a few more geometries. Let's look at, let's say we have methane, CH4. So we know if we go to draw a Lewis dot structure, this is 4 from the carbon plus 4 for the hydrogen. We are at 8 electrons. And we end up with a tetrahedral shape. Now, if we calculate the bond polarities, carbon is 2.5, hydrogen is 2.1. So each one of these bonds will be a 0.4. Okay. Oop. And I actually drew these the wrong way. My dipole should be going towards the center. But however, we discussed in class that the tetrahedron has symmetry. So even though we have this slight bond polarity, it's very small, overall, because of the symmetry, so it's bond polarity for each one is 0.4, but we have symmetry, so overall, the molecule is nonpolar. So it's really important when you're looking at a whole molecule to calculate bond polarity, and you want to analyze the symmetry in the geometry. So that's it. Those are a few key points which I think will help you a lot when you are doing your problems and preparing for your quiz. Good luck.